We will finish this section with one more example in an existence and uniqueness theorem. So we're asked to find the general solution to the differential equation x squared plus 1 dy dx plus xy minus x equals 0. So we do our standard three-step process. First, we're going to write it in standard form. And first, we should notice that there's an x by itself that's not connected to the y. So we would add x to both sides to put that on the other side. And then there's a leading coefficient of x squared plus 1. X squared plus 1 times dy dx. And so we would divide both sides by x squared plus 1. So I'll write that down here. Add x and then divide by x squared plus 1. So what we then get is that our differential equation now looks as follows. dy dx, and then this x gets divided by x squared plus 1, so then we have plus x over x squared plus 1 times y, times y, and then that equals x over x squared plus 1. So what we have here is that our p of x and q of x are the same. So p of x equals x over x squared plus 1, and then q of x is x over x squared plus 1. Okay, second step is we want to find our integrating factor. So we're going to find mu of x equals e to the antiderivative of p of x dx. And so our mu of x here is e to the antiderivative of x over x squared plus 1, because that's our p of x, dx. Okay, now let's do that on the side, that integral, for the moment. So I'm just going to look at that integral, and then I'm going to worry about that e later. So I want to figure out what e to the power x over x squared plus 1 dx is. And I'm going to use a substitution for that. My substitution is going to be u equals x squared plus 1. So that du dx is 2x. And so du equals 2x dx. And And so 1 over 2x du equals dx. So when I use that substitution, I then get my integral of x over, x squared plus 1 is u, and dx is 1 over 2x du. And so now my x's cancel, and my integral looks as follows. It's 1/2 antiderivative of 1 over u du, and that is 1/2 times ln of u plus c. But for the integrating factor, we don't worry about a constant of integration. Okay, so now we plug in what we know that u is. So this is 1/2 ln of, and then u was x squared plus 1. And since x squared plus 1 is never negative, the absolute value of x squared plus 1 is just x squared plus 1. And then we can bring the 1/2 inside. We get x squared plus 1 to the power 1/2, which is the same as the square root. So we have ln of the square root of x squared plus 1. So that's just this part right here, right? We did that integral. And so what we find that mu of x is e to the power, and then that integral was ln of the square root of x squared plus 1. The e and the ln, they cancel out each other out. And so our final answer is that mu of x equals square root of x squared plus 1. Okay, our third step, which seems a little bit scary with a function like this, an integrating function, but we're going to stick to the plan. We have y of x equals 1 over mu of x times the integral of mu of x times q of x dx plus c. Okay, so let's do this. We have y of x equals 1 over mu of x, which is the square root of x squared plus 1. And then we multiply that by the integral of mu of x times q of x. So what we have there is square root of x squared plus 1 times x over x squared plus 1 dx plus a constant of integration. So let's tackle this integral first. So that integral looks pretty intimidating, but it turns out that a substitution that we used before will work here as well. So I'm going to use u equals x squared plus 1. Then I'll skip these two steps and write down 1 over 2x du is equal to dx. So if we use that substitution, then our integral looks as follows. So square root of u times x over u, and then the dx is going to be replaced by 1 over 2x du. So I have square root of u, and then u here, and times 1 over 2x du. Okay, let's clean that up a little bit. The 1/2, we can pull that outside the integral because it's a constant multiple. The x's cancel out, and so we have square root of u over u du. Okay, so now just realize that square root of u is just u to the power 1/2. And so we can simplify this a bit more as follows. We just think of this as u to the power 1/2 over u, and that's the same as u to the power 1/2 minus 1. So this is 1/2 times the antiderivative of u to the power negative 1/2 du, and that's just a power rule. So we have 1/2 times u to the power negative 1/2 plus 1 over negative 1/2 plus 1. And then normally we would also have a constant of integration here, but we already have that here, so we don't need to worry about that. So this is u to the power 1/2 over 1/2, and that 1/2 here cancels with that 1/2 in the front. So in the end, this is nothing else than square root of u. And of course, u was x squared, so that's our integral right here. So let's plug all of that in. So I have let's see. I have y of x, y of x equals 1 over square root of x squared plus 1. Then this whole integral is equal to, this integral here was square root of x squared plus 1. So I'll write that here. And then we still had that constant c. And now you see when we distribute this, these two cancel. And so this is going to be 1 plus c over square root of x squared plus 1. And since we're not given an initial condition, we cannot figure out what c is. So this is our final answer. Now, finally, we can talk about existence and uniqueness of the solution. Basically, the way we proved our formula for solving these linear first order equations, we get this result for free, an existence and uniqueness. You could also use theorem 1 from section 1.2 to prove this. So again, this is sufficient, not necessary. So if p of x and q of x are continuous on an interval a comma b that contains the point x naught, then for any choice of initial value y naught, there exists a unique solution y of x on the interval ab to the initial value problem dy dx plus p of x times y equals q of x with initial condition y of x naught equals y naught. And this solution is given by formula 8 for a suitable value of c. So that's this formula that we have over here. Y of x is equal to this. And then, of course, mu of x is e to the power p of x dx.